Perfect. Thank you very much. Because the time for us is now. There was 120 billion US dollar of investment in renewable energy just last half year, according to Bloomberg. And the question we want to address now is what is needed to get these gigawatt assets to the grid for effective installation operation. And our common denominator is levelized cost of electricity. It is on us to make the parameters efficient. Obviously, we are not the financing guys, so we don't have the pricing and the purchasing power, but we can work on the energy production over lifetime and effective O&M. And all the talks we have seen so far are really going in that right direction. And I can tell you from the data, what we see working with our clients, there's a lot out there to improve. We at Gantner contribute to that whole system with real-time monitoring and control for PV and energy storage. And for example, Europe's largest PV power plant, 600 megawatt, is coming online with turnkey Gantner monitoring all their components. A lot of data, mini resolution, all going to a database, calculated, filtered, so that the customer can do their analysis easily and with open APIs, which is already addressed as an open, because you have to be transparent when the customer wants to do the report and filtering. So I want to share with you along the value chain different interesting observations. What you have seen, it is weather prospecting, PV module analytics, PV power plant analytics, and how machine learning fits in there, and also how we can connect the systems to the smart grid and what is important there. Let us start with weather prospecting. When you want to install gigawatt sites, like here, this location you see on the picture in Arizona, you need reliable information for optimum energy production and output. And we have here a weather prospecting site, 1 Hertz data streaming more than 18 months to the cloud with all reliable sensors from direct diffuse, horizontal, different orientations and all the weather running off grid there. And I just plot the GHI with a heat map filtered for 100 watt per square meter to filter that out, what everything is below that. And you see here that there's also a lot of vertical lines there where the weather is different. So localized weather may help. When you have that data, you want to start to check, and there's nothing easier than you can just compare your measured horizontal radiation versus the diffuse plus the direct component with the angle. And when we plot that, we see this heat map, blue and red over time, and that's quite surprising that this is not matching up. There's plus minus 4% of difference from the calculated divided by the measured, so that's the ratio. For sure, you see the vertical lines there coming from soiling. So I indicated there with some lines when there was maintenance and sensor cleaning. That can be clarified where the vertical stripes are coming from. But even when you sort it out, there is some spring to fall difference. What is the parameter for that? So which parameter should I trust now? Is it measured or calculated? This is here modeling as a main topic, but still, when this is not agreeing, plus minus 4%, that will have impact along the value chain. One side does not mean everything. So we compared that with our own research side, where we have 12 years of data, same setup, same high quality sensor. Here we can sort out that soiling and cleaning is an impact because it's weekly cleaned. There is regular sensor calibration, and there is also a good data acquisition system inside. That's the core from the Gantner business. So we should not do there anything wrong. But when you spot on all the lines, even when you would zoom in here in the PDFs later on, there is a change over the day. There is some asymmetric behavior. There is more reddish in the morning and more blue in the evening. That's something which is of interest. And the same, we see over all the years that there is some change, and maybe there is the isotropic assumption for the diffuse. It's not good enough. I leave that questions to that group here. We shared that pictures already with some experts. Some of them are here in the room, but I would be happy to discuss that in the Q&A session, how we should address that when a sensor versus when a measurement versus the calculated values does not match up for an Arizona location. When you have the weather, you want to go into the PV technology, the PV module itself. IV scans are the DNA of the PV module, and they are really important that you characterize that, see where technology improvements are coming from, what are the differences, and how you can characterize further. We at Gantner are using the loss factors model, which are independent normalized coefficient. When you multiply them together, you get PRDC. If you plot that over time, you easily can see where the losses are coming from. This is here again the formula, and you see here the different normalized values. And for example, you get out the percentage power loss due to R series. If you plot that over time, it really helps you, but you can also do prediction and see if my device is different to what it should do based on the environment. When you calculate that over time, like here for each IV scan on our platform, you get the normalized coefficients out there. I just make that bigger here. And then you can really plot, see the deviations there and discrepancies, degradation, or anything. How can that be visualized? Actually, these charts, what I'm showing here, are part of PVLib in one of the next versions. This is a stacked loss over 1 day from a CATL device. And you see here that the losses from ISC, are shunt, are series, VOC, and also the temperature losses end up with performance ratio DC. This is 1 day, 1 minute. You can easily see where the losses are coming from. And if you plot that over time, you easily see of our data set from here 7 years, PRDC is going down, but the main input comes from RSC in orange, and there is a higher pink area with ROC. So this was RSC, sorry. If you plot that over irradiance, like here and here, you see that for each year, ROC falls at the same rate at all high light levels. But the RSC for this device falls faster at low light level. So with visualizations like that, when you have the data, this type of plots combined with the loss factors give you very fast insight what's going on for long term, but also for short term. Now you don't always have IV scans, you don't always have all that 6 parameters. It works also with 4, just VOC, ISC, IMP, EMP. So you don't always need IV scans. And then our question was how we can use that concept for utility scale monitoring, because you cannot wait and always scale up from one device. We were choosing there a mechanistic approach. What does mechanistic mean? We call our model mechanistic performance model, and it is like that you assign meaningful normalized coefficients that are expected to the performance behavior, and with that you want to fit the observed measurements with understandable loss coefficients. So there is, for example, here 5 parameters, factor C1 up to C5, which are representing a behavior, and they are independent mechanistic. So C1 is the nominal power or the tolerance, temperature losses, R shunt, R series, and wind. You see that here, also part of the PVLib library that you can plot that here. For example, for 75 Celsius temperature and different irradiance in green, you see that temperature losses are quite going high. And here you see the different losses where they are coming from. Comparing to 25 Celsius, temperature are not there because it's constant. And then we have here just the VOC drop at low light. So the MPM, our model, fits very good versus irradiance and module temperature, gives physical meaningful results, and you can also predict the performance. So if you have satellite data fitting into that, you can say what I expect from the component there. But life is not always as easy. You don't have always power plants which are designed as they should be. There is also clipping. There is also real world behavior which is not symmetrical over day. So we improved the MPM to the next level. We call it the professional, where we also cover for asymmetric behavior over the day and inverter clipping. So we can fit that. Asymmetric means still when you fit out the temperature losses, there is a different behavior AM to PM. If you really look at the data you see there, the answer, I'm happy to discuss that, but it's really very interesting that you see that all over the sites there, and the question is what kind of factor and root cause it is. So that's why we can correct for that, and then we do the inverter clipping. So we have a coefficient for that, and then we applied that for PV power plants. This is an 8 megawatt site with bifacial modules, 5-minute averaged input values. And you see, and it's filtered for stable irradiation, so that's why the green is not perfect. We have temperature in red. We have in pink normalized PAC, which has a horizontal behavior at 82%. And then we have in blue the PRAC from the inverter itself, and in yellow the fitted coefficient. This gives, with the MPM professional, a root mean square error of 2.3% for that PV power plant. Plotting that over irradiance, you see that it is like you expect, and PAC is getting horizontal, PRAC is dropping, and the fitted coefficients have to follow that. Of course, normalized VDC goes up as the current will go down. So this allows us to run this behavior on utility scale PV power plants. This is running in the Gantner web portal as well, where we have here plotted also over the day the difference in green and the normalized PAC in blue, and in gray the fitted coefficient. So that helps to quickly identify the losses. But this is not just one measurement, and it works for this parameter. We really have here the possibility that this works for each component in the PV power plant. So it works for a string, for an MPP tracker, for all several hundred inverters, and up to the site level. So you really can optimize that, and it helps you to have like a digital twin for each moment how it should behave. And when you have that difference and you sum it up for kilowatt hours, you can easily convert that into dollars and say, that is my loss, and then start to do your O&M strategy for the electrical losses. We did that coefficient here for several PV power plants. They are across UK, Germany, Netherlands, Denmark. And here there are PRAC on inverter and also on site levels. And you see that the root mean square error of that are in the range of 1 to 4%. The results of that coefficients are impacted by the PV site design, the data quality, and also how the data aggregation is there. It has to be synchronized and so on. So we take the data, fit the MPM, and get this type of coefficients. Where there are empty spaces, there is nothing in terms of inverter clipping. And here, this site, for example, in Denmark, has inverter clipping and some asymmetric behavior. For the MPM, as they are meaningful and mechanistic, the C1 plus C4 should give roughly 100%. Otherwise, you are doing something non-physical, because the nominal power plus the highlight behavior at STC should be ending up at roughly 100%. So we try to really come here to the coefficients that you can use that over time. MPM can not just do PR, it can also do normalized VDC. The fit is very good. This is a 8 megawatt site, the same what we have seen before for a particular inverter. RMSE is 1%, and of course the noise comes from the current and so on. It's very important that reliable results are coming from sensors that you trust, that they are cleaned, sanity checks, and also stable conditions. So KTX, KTH, KTI is very important that you look for that and then start to do the fitting. Now, someone could say, okay, that's good. Let's do machine learning. Of course, we also play around with machine learning, and we try to see how they can contribute to that and how they can add up to the existing. performance. This is a 50 megawatt site with 15-minute averaged values. And you see here the root mean square error in the range below 3% from measured versus predicted. This is running XGBoost algorithm with training. And even when you, and with successive samples over 100 days, and then you are quite fast to get here residuals very, very good on a daily basis. This is a U-shaped power plant, so it's not so easy to, it's a lot of effort to separate that into fields. So we tried that here. Even when you would go for random, the numbers would be below 2%. Machine learning can give you here insights, but it doesn't tell us why these losses are there. So that's very important. But what is more interesting is unsupervised learning, that you bring the data set and ask the algorithm, do you think there are faults? What is good, what is not good? And this nice chart here separates in the red line outliers and true values. Suggest that, and the blue shift is always a 5% difference. So that really is helpful for data sets when you have them, screen them, and let also ask the process what can come up from there. With University of Cyprus, we did run, and we are working and running all the different machine learning algorithms, what I wrote up here, against each other. They have all benefits, advantages, limits, and also different effort on implementation. But if you have the metadata and the API there, and you work with normalized data, it's quite fast to have your. So we try always to follow here the things, and also try to use with XGBoost fault classifiers that you can quickly identify faults. That's quite helpful for O&M persons when they have no idea. In the morning, we can suggest here was a fault, have a look, so that they get an additional information in. But at the end, to understand all that PV power plant behavior, it doesn't help if you cannot connect to the grid, if you don't contribute to the stability. Luckily in Texas, there was no issue this summer, but we had a lot of news in the spring with all the frequency. And we did run on our own Gantner asset here frequency plot with 10 hertz of data over a month in February, running that on our Jupyter Lab notebook in the cloud, and plotting the heat map over February, and on the y-axis hour of day. And you see here in the red shift that there is always a frequency drop. That's 49.9, 50.1. And these red shifts are always when at the energy exchange, the new demand cycles and contracts are kicking in, frequency goes down. So we have to work with a smart grid of the future with all that data, contribute to that, and also react to that. So that's why real-time control is very important, that PV and also energy storage can handle with that and have data exchange. Stable frequency keeps the lights on. This is what we should not reduce the predictability, but we should really contribute to that. Now, running that in microgrid, we did that also with different generation, consumption, and also different loads. This is the University of Cyprus campus. For those of you who have not been on holiday in Cyprus, it's roughly the size of 3 times Rhode Island in the Mediterranean. A lot of sunshine, but it's an island. And you see here that the frequency has much higher variation than the plot before. It's running on generators. It doesn't have a fixed link to the mainland. When you have that microgrid over time, you really want to see how you can optimize the energy flows there. And that's why we installed there our data acquisition concept and control concept. So we get data from all the different PV, energy, EVs, and the grid. Subscribe with the industrial protocols there. Want to emphasize here that OPC UA, for those of you who have not touched that, that's replacing Modbus in the midterm future. self-describing, has all the metadata with it. So that's something to watch for. And then you have that in the real-time controller where you can run the algorithm on it and also change it. You can send then up the data to the cloud, which is based on event sourcing and real-time enrichment. It's not a database, it's like a data streaming platform. And real-time enrichment means for each timestamp, we calculate, for example, power is current times voltage, and you do all that aggregations, you do all that energy equilibrium. So you have that even for kilohertz data. That helps you to be ready for that. Then we do that into the indexing, and then you can access that with Jupyter Lab or our Python platform, run your modeling there or your schedulers and send data back to the system itself to optimize it. So this is the platform what we offer for our customer. And the main benefit of that is that we say that we try to make data scientists more effective because you don't have to sort out the database issue. You have an API which is structured, which is scalable, and you can also import third-party data to that. So we have touched a little bit of hardware, how you can get that done. Let me share some lessons learned, which we also had to work hard for. And I think it's clear for all of us that real-world performance data cannot be accelerated. So really trust your sensors, make sure you get the data on time and do some O&M. And even when this is a modeling workshop here, I would suggest really also measure, not only model, because we see that when we have precise and reliable measurement, we can also do good analytics out of that. You cannot correct the quality with our modeling. It's really depending on good input data. And make also sure you understand the dependencies. You remember the DGA relative chart over time. When you have that sorted out, you also know what's going out at a new climate. Structured and scalable data processing. This is essential because having CSV is not something what will scale over time. We did here already several times about APIs, open things that is traceable what's going on. And of course, do automation. And I think for the modeling for industrial usage, it's really important that you run the models against each other. Don't take the first one at PVLib, really compare it, understand it, and then combine it with the right combination of physical meaningful things like the MPM and also a good classification and detection systems like machine learning platforms are offering. And then I want to conclude with Mr. Deming's words that without data, you're just another person with an opinion. So I think it's on us that we should know the weather, we should know the technology, we should know our O&M strategy, and also the PV output. And then we really can produce and generate continuous profits for our customers. And that will help us to make PV faster growing around the world. Thank you very much.